This is a topic that I'm really excited to talk about because it's something that I've just been entirely focused on for the last 2 years. I think of the time that I've been doing data science as probably having been broken into three periods. And we're in the middle of the second period and we're just transitioning into the third, which is how do we take predictions that are being deployed at scale, and how do we make sure that they're actually solving real world problems as well as possible. And so I said there are three. This is the third stage. So what's come before this? So the first stage, which ended probably 2 or 3 years ago, but was where we were when I got into the field 10 years ago, is one where everyone was experimenting. We had some things that they weren't solving like real world problems. It wasn't like the world needed a better computer Go player. But at the same time, they were really impressive. They captured our imagination, and they caused data scientists to do lots of little projects and enjoy experimenting. And they caused businesses to be willing to hire data scientists, even if we weren't doing something that was impacting them on a day-to-day basis. They would hire data scientists just to do experiments that were sort of related to their business, as a way for them to just build that skill internally. The by the way, so the picture on the right is from OpenAI. There's a project that OpenAI did a year or two ago. I know that Sophia used to work in OpenAI, so I hope this doesn't offend her. But this was, they put really, really smart people, the best AI researchers in the world, a lot of their time, an immense amount of compute, and they trained a model to be really good at the video game Dota. And so I think of this as it's cool that we got to do these experiments, and at the same time, it's sort of a shame that we were doing it in a way that didn't solve many real world problems. And at the same time, a year or two ago, we really started to see a shift in the field from no one was willing to hire you indefinitely to just do these sort of fun experiments. And it became an expectation that your models get deployed. So if the first stage was we're just going to all do experimentation, a year or two ago, there was a change. All of us expect our models to be deployed. And if you're not doing that, then businesses are really disappointed with the results. And deployment was really hard a couple of years ago. It's become much easier today. Amazon has a platform called SageMaker, which is part of AWS. Google Cloud has a few different tools that help you put models in production. Azure, that's this upper right of these three logos. Azure has Azure ML Studio, which again makes deploying models easier. And so in some ways it feels like we're in the golden age of tooling. And there are a bunch of other, they're called ML ops platforms that make it easier to deploy models. And so in some ways, we feel that, all right, we can finally get these things in production and do it pretty quickly, or get these models deployed so they're usable at scale. And at the same time, I've seen a lot of the businesses that have put models in production take the models back out and frequently take them out really quickly. I've seen a lot of people who are really, after being in this field for some period of time, are starting to get disenchanted with the way that we are doing and using machine learning today. And the reason for that is that machine learning is being used to make predictions that are generally pretty narrow. So here's an example. And this is an example, I know several people who are pursuing this workflow. And so if you work for, let's say you're a data scientist who works at for a hotel chain, the type of model you might build today can say for future hotel rooms, let's say hotel rooms on the evening of October 1st, we predict how many rooms will sell in the next 24 hours at any given price. So the data scientist can build a model, and it can tell you that if you charge $150 a night, 10 people will book the rooms, or if you charge $200 a night, 5 people will book the rooms. But that doesn't actually tell you what you should do. It just sort of tells you what your options are and gives you a little hint about what you should do. But for a hotel, when they set prices, the thing they really care about is, well, we're going to sell the leftover rooms tomorrow night and the night after that, all the way up to October 1st. And if you're not helping me optimize my pricing to get as much money as possible, then this is a very, very partial solution. And that's why you see so many businesses, why it's so common for businesses to get the models deployed and then either say, we don't really care, I guess we'll just leave it there, or we'll actively pull it out of production and stop using it. And so where are we? Well, we started with a world where all we did was prediction, but we didn't even hook it up to the rest of our systems. And so it really had no impact. That was this experimentation phase. We are now sort of, I think, reaching the end of a stage where our goal is to get our models deployed. Well, we make a prediction, but then we have some very crude rule of thumb for we've got a prediction and we just apply some other function to that to help us determine, in this case, what price we actually set. But it's no rigor went into that, and we don't have the tools, either conceptually or in terms of software, for us to really ensure that we're using those predictions as well as possible. And the transition we're making now is one where we go, okay, we've got predictions. We are now going to apply as much thought and rigor to how we use those predictions and really formally optimize what we do with them so that we are making ideal decisions in whatever problems our business faces. Okay, so everything I've said right now, up till now, is really, really abstract. I'm going to sort of swing the pendulum to the other far end and say, all right, what does this look like as a practical, real-world example? How could we possibly do this sort of optimization and get to ideal decisions? Okay, the use case I'm gonna walk through, to be honest, is not what I think of as the sexiest or most important use case in the world, and I would choose it almost for exactly that reason. It's something that's been around. So many data scientists have worked on this, and the workflows are so ingrained. And yet, I think, and so if you've been doing ML for a while, you'll probably have seen this use case. Okay, so the use case here is customer churn modeling. An example of how this would get used is, you're a data scientist, you work for a cell phone company, and you build a model to predict who's going to churn. Where in this case, churn means they're going to cancel their service in the next month. Okay, this chart, or this table rather, for people who've been doing machine learning for a while, this is called a confusion matrix. It should be super familiar. Some of you are maybe just getting into the field or developers. So I'm going to try and walk through it very quickly, with the caveat that while it's familiar if you've done it for a while, many people joke that the reason it's called a confusion matrix is, I guess, the obvious reason. But that's not the real reason. Okay, so the way this works is we've got a prediction. Some people, we say they're going to churn, as in they're going to leave the service in the next month. That's this top row. Some people, we say the model predicts they won't churn. That's this bottom row. Some of them, if we waited that month, we saw they actually churned. So that would be the top left is we said they would churn and they did. Top right is we said they would churn in the next month. They didn't. Bottom, I'll do bottom right, which is, I guess, the other easy one. We said they would not churn. We said they would stay with the service, and we were correct. Okay, so that's sort of the structure of this. The fact that we almost always look at this in terms of a prediction on one axis versus the actual outcome, I see the reason for that. I think that there's a sort of hidden danger, or there's a way in which the way we're thinking about it when we phrase it like this is already a little bit academic instead of practical or applied. Okay, so I'm gonna just change the label on the top axis. The numbers aren't changing. There's a very small change. Okay, so before on the top, on the rows is still the prediction, but instead of what actually happened, instead I'm going to say, did we take action on these people? Okay, and so actually, I screwed this up. It should have been take action on the rows rather than on the columns. But we want to say of people when we use the model, the thing we care about is not what did the model predict, but it's if we took action based on the model's predictions, what fraction of the time would that action have been right and what fraction of the time would it have been wrong? Okay, so there's a hidden piece of this, which is that when you get a prediction, that prediction in practice is not purely yes or no, but in machine learning for this so-called binary classification problem, it's a probability. And we get to choose how we translate that binary probability to do we take action or do we not take action? So we could say we're only going to take an action to keep these customers. Frequently, that'll be something like everyone who we think is very likely to churn. Maybe we email them a special offer, and then later on we call them and say, if you stick with our service, we're going to give you $10 a month off for the next 6 months. And the idea is that's going to reduce churn. Now, you only want to do that for people who are actually going to churn. Otherwise, you're taking someone, they would have paid full price, and you're spending effort calling them, and then you're giving them a lower price. And so that's sort of the underlying idea for why we do these churn models. But we can say I've got a bunch of different people, and I've got a distribution for predicted probability of churning, and I can choose, do I only call people and offer them a discount if they're 99% likely to churn, or is it if they're 90% likely to churn, or is it if they're 50% likely to churn? And so we have that flexibility for how do we take action given the probabilities for each individual person. A very natural thing to do is to say, as I change that probability, that changes who I take action on. And as a result, it changes this table here of how many people did I actually contact and what was the disposition of them. Did they actually churn? Did they actually stay? And we can create, I'm going to move towards something, I call it a profit curve, some people call it a revenue curve, but the underlying idea is for each of these different categories of people, we offered them a discount or we didn't offer them a discount, and then they churned or they didn't churn. For each of them, we're going to say, well, what is the dollar value to the business of contacting someone and saying, hey, we'll give you this discount for someone who actually would have churned, okay? So that could be this upper left, this in the bottom table. We say every time we do that, the value of doing that is $10. Every time we do that and the person wouldn't have churned, maybe we say the cost to us is $1. So I'm sort of making these numbers up, but for what the exact dollar values are, but we could just go to the business, someone in the business and say, every time you offer this discount to someone who otherwise would have churned, how much is it worth to you? And they can give us these numbers. And now we can just do some multiplication and subtraction and say we had 50,000 people who we took action on, they would have churned. Every time that happens, we think the value to us as a business is $10. So on the top, I've got 50,000 people at $10 each. And then you say, well, some of the people I offered them a discount, they wouldn't have churned anyway. And so I've got, that's where I get this minus $30,000 times 1. And so I can say, if I use a certain threshold to determine how many people are in each of these buckets, or in each of these cells of this table, in this case, it would have been delivered $470,000 of value to us. But remember, we can move this decision point around and get different number of people in each of those cells, and as a result, get different values. So this is really just an arithmetic calculation at that point. So I can test out a bunch of different decision thresholds and say for each of these decision thresholds, that is ways of converting my prediction to who I take action on to value to the business, how much value did that deliver? And you can see it, you know, if I plotted that out and it looked like this, you'd say, maybe I should reach out to everyone whose likelihood of churning is above 20%. And you could plot out this curve. It's a pretty straightforward thing to do. And then you can get an optimized way of turning those probability predictions into decisions about what action you take. I really, really like profit curves. I think they are a very first step into how we think about taking predictions and doing something smart with them. At the same time, it's still a little bit crude. I think it's like, maybe the right way to think about it is 20% of the effort we need, and it provides maybe 80% of the value of going from what we do today to being really rigorous and optimal in how we use our predictions. Something which is a step even better than that, and this is something that's sort of embedded in the company that I've built and the software that we build, which I won't go into, is for each customer, when we say, what is the cost of providing a promotion to them? And that could be different for different customers. We can say, what is the revenue conditional on the promotional effort, where we think about the discount? What's the cost of providing service to them? So an example is, it could be that there are some people where the cost of providing service to them, either because of how much they use the service or where they live, it could be that it's so expensive to provide service to them that even though you think they're going to churn, maybe it's not worth offering them a discount because you're just as happy if they churn. And so that's this sort of service cost at the bottom. And yeah, so we could build out, and you could do a simple version of this even with a spreadsheet and say, what's the cost for each customer? What's our revenue if we offer them the promotion? What if we don't? And then we can turn this into a profit. And we can do that at a customer by customer level, and then reach a decision rule or about who we reach out to that is a little bit more optimized or a little bit more customized to the customer than just a simple threshold, and say everyone above some probability according to the model we reach out to, everyone below it we don't. But this still is using, when we say what's the likelihood of them churning, that's still using our machine learning model. And then the way that we do this is we use the machine learning model to say, if we offer them the promotional discount, what's the likelihood that they stay? So that's in this left table, the second column. If we don't offer them the discount, what's likely they stay? We can then calculate the profit of keeping them if they stay for both of with and without the promotional discount, add it up over some period of time. And this year, this is just arithmetic, so I won't walk through it. But we can, for each customer, do this calculation and say, what's the value to us as a business if we offer them the discount? What's the value if we don't? And that's a combination of some business rules and the machine learning model saying the probability of staying. In this case, we'd say our total expected profit over the next 6 months is greater without offering them the discount. And so we choose not to offer them the discount. We'll make these slides available. And so if this was something I don't know whether I went through this too slowly or quickly, but you could sort of see how the profit of them staying depends on whether we've offered them the discount, and sort of see that this is just multiplication. All right. Where is this useful? Personally, I think this is useful in the majority of cases where we are using tabular data, data that's stored in tables, to make to make predictions. I think, and I've talked to a lot of data scientists and heard a lot of use cases. In most cases, they've told me at the beginning of the conversation, yeah, the way we use our predictions, we think it's pretty good. And then we talk about it a little more, and by the end they go, we're actually putting all this effort into predictions, but we're leaving a lot of money or efficiency on the table by not going through this next step of rigorously optimizing from our prediction to our action to the thing that we care about at a global level. So let me give you some examples. Fraud prevention. So I spoke with someone not that long ago. They are predicting which insurance claims for US insurance markets, which insurance claims are going to be fraudulent. Something which many people do today is they just say everything above some threshold, we refer and investigate and potentially avoid paying that fraudulent claim. But even a very simple rule would be to say, we look at the amount of the claim, so that if something is sort of medium likelihood to be fraud, but it's like a very expensive claim, a $250,000 claim, maybe we prioritize that over something that's more likely to be fraud, but it's a $1,000 claim. And so there are other dynamics that we could incorporate that into that. You get something similar for product recommendation, which is a really widespread use of AI. But when I go to a website, instead of just saying what's the likelihood that I'll buy something, we should think about, well, if I buy it, what's the likelihood that I'll be really happy with it, or that it'll cause me to return, or that there's a big profit to the business of me using it. The two that are over here on the right are probably the ones that I'm most excited about, because it's not just making more money for the business, but it's actually just making a more efficient world. Preventive maintenance. We've got a manufacturing line. We have sensors on some of the devices, like a drill bit. And the way that these sensors are used today is we ingest data from the sensors to predict the likelihood of that drill bit failing. And then whenever it reaches above some threshold, let's say 20% likelihood of failure, we just proactively replace it. But there are some points in the day when if you take that machine offline, it bottlenecks your whole factory. And so you just produce less stuff, and you're just less efficient. And there are other points in time when, because of what's happening elsewhere on your factory floor, if you take that machine offline, proactively replace it, replace the drill bit, like it doesn't bottleneck anything, and it doesn't affect your production for the day. So the things that you should think about are not just, is the drill bit about to fail, but I want to weigh the trade-offs of, should I proactively replace it now versus what's the impact on my efficiency manufacturing as a whole if I take it offline. I've always thought, like, if we could make shipping 5% more efficient, which I actually think, machine learning has the potential to do, but the way it's being used today is not really going to get there. If we could make shipping 5% more efficient, like the impact that would have on global carbon emissions would be like just vastly more than, it would be huge. It wouldn't really require sacrifices, and yet to use machine learning for supply chain management and how we do shipping is a really hard problem, because if I say, what's the likelihood of something getting delayed, I need to think about, well, if it's delayed, how does that impact its ability to make the next connection? Because shipping, a lot of times you've got these connections, and so you've got all these sort of processes where just knowing, should I ship on method A or method B, which of those is likely to be delayed or likely to arrive by a certain time, I really need to think about what are the downstream impacts of that. And you can do that through simulation and through processes which are not that different from what I've shown you. And so I've always thought supply chain management is something I'm just super excited about, and really hope that the data scientists of today who are using machine learning but aren't yet making the world vastly more efficient in terms of supply chain management or preventive maintenance, that we're able to then layer on an optimization layer and just make these processes vastly more efficient. So yeah, I went through that, I think, pretty quickly. It's all stuff that I'm super excited about as a technique, and so hope that there are questions that just we can talk through and make it clearer.
Okay, thank you very much, Dan. I see we have questions from our community. So they're in the chat, so then you can see them too. So how do you compare the econometrics approach and machine learning approach to analyze data? How can I study machine learning in a proper way using what I already know from economics background?
Okay. Let's see. So, okay, econometrics versus machine learning. So in some ways, I studied in grad school. I studied econometrics, and even within econometrics, there are different branches. Econometrics broadly is really, really focused on understanding causality. That's especially true of so-called, reduced form econometrics, where people do instrumental variables. So they're really focused on how do I know a cause and effect relationship? And they are willing to make predictions that are less accurate in order to get a sense for causal relationships. Machine learning, the machine learning community, there's a small division of it that thinks about causality, but for the most part, we just say the machine learning community is just very focused on making accurate predictions and doesn't think about causality. I think as an econometrician or economist, how can I study machine learning in a proper way using what I know from economics? I think that, to be honest, I think that you will do it by accident, as in to say, if you just go in and learn machine learning the same way that other people do, sometimes people who are using machine learning will try and use it in a way where they're sort of assuming that they can make a change and have this causal impact. And you will say, that's not right, and I know that's not right because of what I've learned in economics. And I think that in the long run, the machine learning community is probably going to get better at econometrics, or better at recognizing when they're relying on causality mistakenly. And I know the economics community, which I'm less tied into than I used to be, is now starting to use machine learning. And there's some papers and techniques by Susan Athey that start to combine these. And so we'll see more of these combinations. But how do you learn to be effective? I would honestly just start by learning machine learning, and I think that you on your own will probably pick up on some of those connections.
Cool.
Yeah.
So next question is from Peter. Where do you see the intersection between observational studies using data and machine learning with control experiments? Who is making it easier to blend the two? Yeah,
I mean, and this ties in so closely with Alfonso's question. Observational studies where you frequently apply machine learning are not great for determining causality, or some people would say are terrible for determining causality. The thing that I think about a lot is what parts of the world are changing and what parts are staying the same. And so if, for instance, one of the there's a lot of use cases for machine learning for radiology. So it looks at a scan and then it says, does this person have whatever, a certain disease? Okay, so for that, like the world's not changing. If I have the picture, that gives me all the context that I need to make a diagnosis. And so that's a case where observational data is just fine. And we could think of things that are tabular data that work the same way. In other cases, the environment is changing very, very quickly. In 2020, that's probably most of the world. But if I said, what is the likelihood of a shipment arriving on time? And how does that change as I put more weight on that flight or less weight? To the extent that flights have a different number of people and their different security procedures, it's really important for us to be able to understand the causal relationships. And data that was collected in 2019 observationally is not going to be that useful. And so I think controlled experiment, really useful for causality, which is especially important as we start making applications to new circumstances. Observational data is great for making predictions, and predictions in cases where the world's going to continue looking like it has looked, or our domain's going to continue looking like it's looked. Predictions frequently are pretty good, and I know most people have a violently negative reaction to this, but I actually think in some cases observational data is fine for causality if we understand how the observational data was generated, and we think that process is going to continue being the same. Okay, the next question from Dave. What do I think are the pros and cons of the different ML ops platforms? I don't know. I've not, I know that SageMaker exists, but I've never used it. I know that Azure ML Studio exists, but I've never used it. I've used some of the Google stuff, but I just, yeah. So and then there are a bunch of other platforms. Yeah, the short answer is I just don't know. Sorry.
The next question from Neeraj.
Does the fact that people are not following through with this kind of decision making suggest that there's a limitation in current ML or optimization techniques? You know, the way that people, there's an ML community right now. They make predictions, and like I said, I've talked to a lot of data scientists now, and most of them just don't even think about optimizing the outcome of that. And so I don't know that it's a problem with, I mean, there's a problem with the ML techniques in some sense, but really the problem is that we don't even worry about using predictions as efficiently as possible. Or another way of saying that is, if I asked data scientists, what fraction of your time do you spend thinking about the optimal way of going from predictions to decisions, I think it'd be very, very rare for people to say more than 5%. So there's a limitation in techniques, but really it's just we're not paying a ton of attention to it. And then the flip side is optimization. You know, most of optimization is happening in the operations research community. They use really, really simple models of reality and can't learn complex equations the way that machine learning can. And so for the most part, the operations research community is almost, I think, been left behind in that there's just not a lot of excitement about it. Data scientists aren't aware of optimization research techniques. There are very few companies that are out there like hiring OR, operations research experts. And so I think we need to combine these two. And that's both in terms of the techniques, which is the stuff that I'm sort of working on, but also just reminding each of these communities about the benefits of the other community and the shortcomings of what they're doing, so that you can have this sort of cross-pollination. And so there's a shortcoming in the techniques that they don't use each other, but some of it is just the shortcoming in the way that we think of the way that we think of these and how separated they are. We've got a question from Dave. Once customers learn that discounts are offered, if a business thinks a customer will churn, won't customers demand a discount? I've never paid more than 1/3 of the list price for SiriusXM for this reason. Yeah. Well, I don't know whether Dave currently gets a discount from his cell phone, his or her, their cell phone provider. But I do know that cell phone providers offer these discounts. A lot of companies are offering these discounts. And I don't know how many of us, I pay full price. Even I go for full price, even having been part of more than 10 of these model building exercises. And so maybe I'm just less savvy at that than Dave. But I suspect that most people are not being that strategic yet, and maybe will become more strategic. But a lot of companies are doing this today, and very few of us, I think, are using it as strategically as Dave is. There's a question from Andrew. Do you think it's worthwhile to attempt to reconfigure the prediction targets to be business actions themselves? Offer a discount or don't offer a discount? Have I seen this work? Yes, this is a great question, and it's a question that since I've sort of started focusing on this, that I've heard a lot. It sounds like it would make sense, but it doesn't quite work. And here is the reason. When we set a prediction target, we're just looking at data that's been accumulated from the past. And so if I said my prediction target is whether someone's been offered a discount, then really I'm just, what I'm doing there is I'm saying, whatever we've done in the past, I just want to do the same. And I want to use my model to get as close as possible to doing the same. But if instead we say, I want to do better than has ever been done in the past, then I can't use a prediction target in the conventional sense of like, look, I've got something in my data that says, well, we offered a discount or we don't, and then use that as my prediction target. Now you could say there's something as a prediction, like I want to say, what should we do? And that's my target. The way ML is done, like you just need your prediction target to be something that you have historical data for. So we can't do that, and we're left really saying we're going to use, if we use our behavior as a prediction target, we're really just mimicking what we've done in the past. Okay, we've got a question. Let's see. Go ahead.
Yeah, from Michael. Will AutoML replace data scientists, or in which aspects it will?
Yeah. So in full disclosure, I worked for Data Robot, which I think probably the earliest big AutoML platform. And maybe that's shaped my views. But I just think that the work that data scientists did that AutoML is replacing is, sorry, let me back up. In the early days of compilers, as in like the language C compilers, they used to be called automatic programmers because people thought that if I did not need to think about how I could write like the C language or something higher level, then we'd all just be so efficient that like we didn't need to think about like how for each individual command, like what memory, what operation do I use to move from like one memory register on the CPU to the other? They thought that like that might displace programmers. It's turned out that the number of programmers has increased rather than decreased in the last 40 years. And the reason for that is that, yeah, there was some work that programmers used to do that was really mechanical, and we've sort of automated where now I write something in Python and it's creating like every line of Python is creating like hundreds of lines of machine code, which is executed on my CPU. But we see more programmers because we can just do more interesting stuff, where we can go and see things in the real world and say, I should write a program to solve that. And the job of the programmer now is really to like translate something which is much higher level and do more abstract thinking about like, how should my program work? It's sort of done by product managers, but still a lot of it is done by programmers. And then translate that not into very low-level machine code, but translate it into Python or JavaScript or Java. And I think the same thing's going to happen with AutoML, where, yeah, we're not going to be picking the learning rate, but we are going to be understanding the use cases and understanding the business, and then matching that with like, okay, what data do we have? Can we rely on this data? And what decisions should we be using? What's the right prediction target? And AutoML is not going to replace that. So it's just going to change the way we work, but it's not going to replace us. And then there's a question below that, which is sort of similar but sort of different. How close do I think we are to having canned ML solutions for common use cases? Yeah, a lot of very smart people think we are very close. I think that's probably closer to true for B2C applications. You know, the thing that when I used to do consulting, the thing that I observed is that everyone's data looks a lot different. And so if I am structuring a problem for, if I'm structuring a problem for UPS, because of the way they've stored their data and all these historical reasons, I think it's actually a lot of work to then translate that to DHL. And so I'm just quite skeptical that you can have canned ML solutions that are going to be like whole big picture solutions for for a lot of use cases. And even, you know, the question is like what we currently have for ERP solutions. But ERP solutions, they're sort of canned, but a lot of customization goes into how those are used, like an immense amount of customization. And so, yeah, maybe it'll be something similar, but now we're getting back to just generic AutoML rather than it being like a canned, how do I route things for FedEx or whatever.
Question from
okay. Something from Antonio. Can you share some of the resources on which you based your presentation? Was it all based on your professional experience? I'm from academia and I find it hard to find books, courses that tackle this, translating ML knowledge to business value as well as you did it today. You know, again, I don't want this to sound commercial, but I started a business doing exactly this. And the reason that I started that is exactly because I'm just shocked that there are not tools to do this today. Yeah, I mean, and you see these things come together of like the tools or infrastructure to solve problems a certain way, and those tend to go along with like the mindset to solve problems a certain way. And so there's like a part of it which is culture and a part of it which is tooling. And if you have a culture where people say like, hey, we all want to do this, then the tooling, like someone will build the tools. I also believe that, you know, sort of a feedback loop. We don't have the culture to do this because it's hard, because the software doesn't exist. And so I'm trying to build the software to make this process easy and thus have it be widespread. But I don't understand. I'm just shocked that there aren't better resources for how to do this. And yet, yeah, and yet there aren't resources for how to do it. The best that I can suggest is, you know, if you talk to someone in your operations research department, you know, if you're in academia, you go to someone at the business school who focuses on operations research, they can tell you a lot about optimization. They're probably not thinking that much about building really, really accurate models. And if you're on the operations research side, you could go and find someone in the computer science department, or now a lot of schools have data science departments who's doing ML. And so it's just a matter of, in my mind, a lot of it is a matter of combining these two. There's some other caveats that I think are important, but how to get started, it's unfortunately just taking these two literatures and then brainstorming how to put them together. I guess the other, you know, the flip side is if you're in academia, it's important to you to be able to publish. And so maybe I've just given you the formula where you say, I'm going to take 2 articles and put them together, and I think that I think that's publishable. But yeah, I've seen very little of it. We have a question from Peter. Do you see a market for putting one model up against another? So for example, a model to exploit another company's models. For example, a model that predicts when a retail customs model will offer discounted items. Yeah, so I see a big role for that. And you know, I started with this example in hotels. If you wanted to, or I started this story about hotels. Hotels use their competitors' prices from the previous day when they forecast demand. So if their competitor's offering a low price, then they predict that they'll sell fewer rooms. And if their competitor is offering a high price, then at any given price, they think they can sell more rooms. So if you were to do a good job of this process that I proposed, where you say, I'm going to build a model and it's going to account for all these different factors, and then we're going to try out different pricing rules. One of the things you would think about is, whatever price I set today, how is that going to impact my competitor's price tomorrow? Because like, if I don't think about that, well, they're not thinking about that today in any rigorous way, or really in any meaningful way. But if I don't think about that, then I'm really missing this important part of what's the impact of having a higher or lower price today. So the right thing to do, I think, is to take your competitor's historical data, which they have, and to build a model of, here's my competitor's price as a function of many things, including my price. And that's exactly the sort of like adversarial or that's exactly the type of model that I think you've described, where I've got a model of what will my competitor do. This, I guess, also a game theoretic way of thinking about that. And yeah, I think that's going to be very, very important. And another way of saying that is like, if you if you're not modeling that, if you're not thinking about how will my competitor respond to my choice, like you're just missing out on like a huge part of making good decisions in a competitive environment. Yeah. Yeah, and then Niraj has a comment. Yeah, GAN models are frequently used for a different purpose, which is to try and generate something synthetic that looks real, but definitely have all of those same sort of like adversarial parts to them. And the original GAN papers even phrase it in the same sort of like game theoretic language that you would probably use that you could use in a business context, where I say, what's my competitor's price going to be as a function of my price, and how can I think about that when I set my price today?